Let's take a moment to consider how our computer stores variables in memory. We can imagine our memory as a continuous line of slots, each with their own associated number, indicating which slot it is. And in this, we can store our primitives. We can consider another area of our memory to store references, which we'll call the stack and the heap. This is not the full idea of stack and heap. That's a rather complicated concept. We'll do a simplified version for this tutorial, where we will think of it as values and references. Our references can point to a value, and that value can change. It's mutable, and the reference will stay the same. We can also reference multiple values from one reference, and that's called an array. When we create an array, we allocate a certain number of slots from values to a certain reference. Here, we allocate 8 slots to a reference called array of int, and in those slots, we fill it with ints. The blue array, we will call it, starts at index 1, and when we want to resize it, we have to create a new array, starting at a new memory area, and we have to fill it by copying the values from the first array. This is a time-consuming and tedious process, and we have 2 arrays existing in the memory at the same time. When we want to swap it over and make the previous array into the new array, we don't actually change the array. We rather just change the reference. We change the blue array to be pointing to the newly created array, and then we can discard the red array as it no longer exists. It's pointing to the same thing. Now, garbage collection will take care of the old values that we've already copied over and are no longer being referenced by anything, and we have a resized array. But notice that we created a whole new array in memory. It has nothing to do with the original array we created. We copied over all the values, added our new value, changed the size, and then changed the reference. We didn't actually resize the original array. To have a resizable data type, we have to consider something a little bit differently. And for that, we're not going to think about our memory anymore in values and references. Rather, let's just think about memory as storing objects. We have a certain amount of slots which can be occupied by any kind of object that is defined in a .java file. Objects can contain whatever fields we want, primitives or references to other objects. Here, we will consider an object which is able to reference another object from itself. So how can we do that? Well, what if we had an object which actually references another object of the same type, and then we just have a chain of these references which lead us to the next value? Remember, in memory, we don't know what we're looking at unless we have a reference. So let's say we have a reference to a node at 56. Node at 56 stores a reference to another node at 57 and a value. And that reference is key, because that reference points us to the next node in the list. As we travel through our list, we can see that the existence of the pointer reveals to us the next nodes. And as we follow through our list, and we take our time to iterate through and access each node, noting that it actually takes a long time to traverse through this list. So the more nodes we have, the longer it'll take to get to the last one. We can see that each node indeed has its own pointer and value. And as we follow through, as we cascade down the list through the pointers, we can see what happens when we reach the end of our list. At the end of our list, the last node will point to null, because there is no next element. And this is one of the keys of the linked list. It's easy to add a node. All we have to do is change that null to a new reference, and suddenly, we're able to be transported to our next node, as if it was in the list the entire time. This creation of new references and change of references is the core resizability and modifiability of a linked list. It's what gives it its advantage over an array. So now if we follow through our list, we can see our previous nodes were unchanged from this operation. And as we flow through our memory to get to the next node, we can see that the creation of the new pointer has revealed to us that our list is expanded by 1. And now if we check the value and the reference of this node, we can see that since it points to null, it's at the end of our list. And now we've got a linked list that's modified. This is the core useful feature of a linked list and why we create them, and its advantage over an array.